Hello, we are discussing about GATE 2009 ECE paper. Look at the magnitude plot of a rational transfer function g of s with real coefficients is shown below. Which compensator will have such magnitude plot? A. Lead compensator, B. lag compensator, C. PID, D. lead lag compensator. First understand the notation given as g of s. G of s is rational transfer function which will be consisting of numerator as well as denominator polynomial. Numerator polynomial as well as denominator polynomial d of s, for example. And all coefficients of s as well as constants are going to be real in nature. They don't have any imaginary parts. Remember that one. Okay. So now, if g of s is having such behavior, then which compensator will have this type of magnitude plot? Okay. So first we will examine one by one. Lead compensator. For a lead compensator, 0 will be more near to origin compared to pole location. So this will be 0 and it will be pole. Let us assume 0 is indicated with Z1 and pole is indicated with P1. Then the transfer function is going to be looks like g of s will be looks like s plus z1 divided by s plus p1, but z1 is more near to origin in the s plane. Okay, so if you are going to draw the Bode plot of this one is going to be initially. Okay, so this is a pole location p1 and it is z location z1. So Bode plot is always going with the magnitude versus frequency. So as the frequency increases, first you will get the P1, next you will go for the Z1. Till P1, the magnitude is going to be constant, and from P1 onwards, pole will give minus 20 decibels per decade. So pole will be giving minus 20 decibels per decade like this, and from 0, whenever a 0 encounters, and 0 will produce plus 20 decibels per decade, plus 20 and minus 20, both will get cancels, and again you are going to get a constant slope. So this is a transfer function for a lead compensator. So this is not the right answer. Next, come for the lag compensator. For lag compensator, pole is more near to origin than 0. So for example, this is Z1 and it is P1. Okay. Again you are going for the same transfer function, but location of pole is more near to origin than 0. Okay, so this is Z1 and it is P1. So Z1 is more far than P1. So first in the Bode plot, now 0 encounters. So till the 0 encounters, this is the 0 encounters Z1, and now after that one pole encounters. So till this one it may be having a constant slope, and 0 will produce plus 20 decibels per decade. So it will be going increasing, and whenever a pole encounters, that will give minus 20 decibels per decade slope. So total slope is plus 20 plus minus 20, that will be 0 slope. 0 slope is nothing but constant. So this is the Bode magnitude plot for the lag compensator. So this is also not the right answer. Next, if you are coming for this lead lag compensator, generally it is not practically used. You don't find this one in any textbook, and even if you search in the net also, you don't get any information about lead lag compensator. So this is not practically used, and what we are going to use practically is lag lead compensator. Lag lead compensator is more generally used compensator, and lead lag compensator never occur in practice. So this is also not the right answer. So the right answer is PID, but we will prove how a PID can have this type of nature. Okay, so PID controller is going to be having a form of proportional plus integral, which is nothing but Ki by S, and differential compensator. So it will be consisting of proportional term, integrator term, and differentiator term. So if you take 1 by S common, then it will be looks like, okay, Kd into S square plus Kp into S plus ki. So from this one it is a second order. Second order is nothing but it has two roots. So roots of this one is nothing but now the second order equation is in the numerator. So the roots of the second order equation is nothing but two zeros. So it will be consisting of two zeros at z1 and z2 location. Okay, and it has a pole at origin. So this is PID controller. Transfer function looks like z1 z2 are going to be two zeros and a pole at origin. Okay, then the transfer function for this one is looks like, okay, from 0 onwards the pole is going to be at present. So this is a pole and it is z1 and this is z2. So before that one it may be having a constant slope, and after that one a pole encounters at origin, so that it is giving minus 20 decibels per decade till z1 occurs. Okay, whenever z1 occurs, that is first 0, that will be contributing plus 20 decibels per decade. That makes the total effective slope will become 0, because pole is introducing minus 20, 0 is introducing plus 20. Total effective slope will be 0. And next this happens till z2, and after z2 again the slope is going to be introduced by z2 is plus 20. So now the effective slope is plus 20 decibels per decade. So it will be increases in this way. So the transfer function is now looks like the given magnitude plot. So the right answer is PID compensator. And you may be confusing from this one. This is minus 20 decibels and it is, this is plus 20 decibels and it is minus 40 decibels. So the difference between these two things is 60 decibels. Okay, but here what we are going with is slope, the change in these 2 points. The change in these 2 points is going to be 60 decibels, but what we are going with is this is having minus 20 dB per decade slope and this is having plus 20 dB per decade. So don't confuse with slope and with the values, because there may be a difference of 3 decades. Between this point and this point there may be a difference of 3 decades, and again between this point and this point there may be a difference of 3 decades. So for 3 decades if it is 60 decibels change, then for 1 decade it is 20 decibels change only. So don't bother about the slope of this one. Okay, only the shape of the magnitude plot is important. So the right answer for this right answer for this question is PID controller. So C is the right answer. Thank you.